The vapor compression refrigeration cycle. In this section, we consider the ideal refrigeration cycle. For a working substance that change phase. During the cycle. In a manner equivalent to that done with the Rankine power cycle in previous section. In doing so, we know that state 3 in the figure shown here state 3 is saturated liquid at the condenser temperature and state 1 is state 3, and also we have state 1 is saturated vapor at the evaporated temperature. This means that the isentropic expansion process from 3 to 4 isentropic expansion process will be in the two-phase region. And the substance will be mostly liquid. As a consequence, there will be very little work output from this process. So it is not worth the cost of including this piece of equipment in the system. Near zero, very little work. So it is not worth cost of including the piece of equipment in the system. We therefore replace the turbine with a throttling device. throttling device. Usually a valve or a length of a small of diameter tubing. A valve, small diameter tubing, by which the working fluid is throttled from the high pressure to the low pressure, from P high to P low. Saturated with air at the pressure enter the compressor, undergoes a reversible compression process 1-2 seconds. This process 1-2 process reversible adiabatic. Compressor. It is then rejected at constant pressure in point 2-3 in stage 2-3. The working fluid exits the condenser. It is rejected at constant pressure. And the working fluid exits the condenser as saturated liquid. An adiabatic throttling process. Three, four. Follows, and the working fluid is then evaporated at constant pressure. Process 4-1 to the complete cycle. The full cycle shown in this picture. In this picture, the similarity of this cycle shown at point 1 comparing to the air refrigeration. In the previous picture, I used the heat pump picture. Anyway, we have point 1 as saturated liquid, stage 1 is saturated vapor, stage 3 is saturated liquid. The diagram shown here, state 3, state 1, state 2 isentropic 1-2 seconds, and state 2 to state 3 is heat rejected, and state 3 to 4 or 5' is a two-phase. and 4 to 1 is the heat absorption. The similarity of this cycle to reverse of Rankine cycle has already been noted. We also noted the difference between this cycle and the ideal Carnot cycle, in which the working fluid always remains inside the two-phase region 1, 2, the ideal 1 prime. As we can realize that we have a 1 prime, 2 prime, 3, 4 prime, and 1 prime is Carnot cycle. It is much more expedient to have a compressor handle only vapor than a mixture of liquid and vapor, as would be required in the process 1 to 2 prime of the Carnot cycle. It is virtually impossible to compress at a reasonable rate a mixture such as that represented by state wide prime and still maintain equilibrium between liquid and vapor. The other is process Smith. The other difference, that of replacing the turbine by throttling process, has already been discussed. This part of cycle. The standard vapor compression refrigeration cycle has 4 known processes: 1 isentropic, 2 isobaric, and 1 isentalpic. We have 4 processes. In vapor compression, refrigeration, so we have 1 isentropic compressor. Isentropic and 2 isobaric condenser evaporator. And 3 isentalpic. H constant, throttling. We have 4 known processes between 4 states with 8 properties. It is assumed that state 3 is saturated liquid, as we said before. State 3 saturated liquid, and in this picture saturated liquid, and state 1 is saturated vapor. Saturated vapor and is after evaporator. So there are two parameters that determine the cycle. The compressor generates the high pressure P2 equals to P3 for the isobaric processes, and P4 equals to P1. At cold space, determine the allowed temperature T4 equals to 2T1. The system described in the picture can be used for either of two purposes. The first use is the refrigeration system, in which case it is desired to maintain a space. Consider the picture again. The first use is a refrigeration system, in which case it is desired to maintain a space at a low temperature T1 relative to the ambient temperature T3. Or desire low temperature, for example T1 relative to T3 ambient temperature. In a real system, it would be necessary to allow a finite temperature difference in both the evaporator and condenser to provide a final rate of heat transfer in each. Thus, the reason for building the system in this case is quantity QL is important. The measure of performance of refrigeration system is given in terms of coefficient of performance, COP, beta equals to the second use of this system described in the figure is the second use heat pump system. A higher temperature is desired. Beta equals to QH on W compressor. Coefficient refrigeration system and the heat pump system are of course different in terms of design variables, but the analysis of two systems is same when we discuss refrigerator in this and the following two sections, it should be kept in mind that the same comments generally apply to heat-gun system as well. The next section is working fluids for vapor compression refrigeration systems.